right, so to continue on into quadratics, I'm going to talk about a couple different things today. All right. So one of the ways that we can actually solve quadratics is by just doing inverse operations. Now, this only works with certain types of quadratics, mainly ones that are missing that middle term. Okay, so there's no x term, there's just an x squared term and a constant. So for example, if we had y equals x squared minus 9, okay, this method works on these, and this is actually probably the easiest method to do. Plus, it helps set up for the next method I'm going to teach later on. So, inverse operations, the first thing we have to do is set y equals 0, because remember, that's what we're solving for. We're solving for the x-intercepts, and the x-intercepts are when y equals 0. So we set y equal to 0. Now, we just have to solve for x. So this actually turns into the algebra you've been doing since about 7th grade. Okay, our first step is to add 9 to both sides to get x squared by itself. So we end up with 9 equals x squared. Then we need to undo the x squared. So remember, the inverse operation to squaring something is square rooting it. So we need to square root both sides of the equation. Once we do that, remember that when we square root 9, there's actually two possibilities. There's the positive 3, because positive 3 times positive 3 is positive 9. But there's also negative 3, because negative 3 times negative 3 is also positive 9. And then, of course, the square root of x squared is just x. So you end up with the answer, plus or minus 3 is equal to x. So you notice there's actually two answers here. Now, we use the little symbol plus or minus, but really what that's telling us is that there's two answers, negative 3 and positive 3. Now, remember from yesterday that what this actually means is that there's two places where the graph crosses the x-axis. So let's look at the graph real quick. Okay, so here is the graph for y equals x squared minus 9. Now you may notice that it's still a parabola, which is what we need. So as a vertex, it's positive, so it opens up. So all those things we talked about with the graph with transformations last week is true with this. But notice the x-intercepts. The x-intercepts here are at positive 3 and negative 3. There's 2 points where it crosses the x-axis. That means there's two solutions. And in this case, the solutions are negative 3 and positive 3. Then you may also notice some other things about this type of quadratic. Okay, the y-intercept, remember that's really easy to find usually because it's usually just the constant, negative 9. Okay, and that y-intercept is also the vertex. So the symmetry is around the y-axis. Now, what you may have noticed earlier is that this is also one of our special polynomials. Remember when we emphasize difference of squares? This is a subtraction of two perfect squares. And so this should also be one that's really easy to factor. Now let's look at that real quick. Okay, if we factor this instead of solving with inverse operations, remember x squared minus 9, difference of squares, we just factor into the conjugates. X minus 3, x plus 3. And to solve this, once again, we need to find when y equals 0. And so we set each of those expressions equal to 0, and we solve. And so we still get the same solutions, negative 3 and positive 3. So you could definitely do this factoring. You could definitely do this with inverse operations. And there's going to be some other methods we're going to learn later on that you can do this as well. So this is one of the special quadratics that really any method will work. So let's try another one out. Here we have y equals x squared minus 121. Let's do this first by doing inverse operations. So remember, the first step is we're making y equal to 0 because we're solving for the x-intercepts, and the x-intercepts are when y equals 0. We then want to do inverse operations to get the x to be by itself. So the first thing we're going to do is add 121 to both sides. So we get 121 equals x squared. Next, we need to undo the square. Remember, the inverse operation of squaring something is square rooting it. When we take the square root of 121, there's actually two possible answers. We have the positive 11, because positive 11 times positive 11 is positive 121. But we also have negative 11, because negative 11 times negative 11 is also positive 121. And then, of course, the square root of x squared is just x. So our solution here is plus or minus 11. Let's do this with factoring. Okay, so if we have y equals x squared minus 121, this is a difference of two perfect squares. And so we really can factor this quite simply into the conjugates. Y equals x minus 11 times x plus 11. To solve it, we then need to set y equal to 0. And then since we're doing a product here, and the product is equal to 0, that means one or both of these terms have to be equal to 0. So we set each of those equal to 0. And we solve. And so we get the same solutions, negative 11 and positive 11. Now remember, what these mean is that these are the 2 points where the graph crosses the x-axis. And so you notice from the graph that I have here that it crosses at negative 11 and positive 11. And the y-intercept is negative 121, which also happens to be the vertex. So that's doing inverse operations. Remember, this is really just specifically for these difference of squares for when you're missing the middle term. So a little bit of review. Okay, remember we have 3 different forms for quadratics. We have standard form, which is, like the name says, the standard way of writing it. This is what we're going to see the most. Okay, we've already learned how to use a t-chart to graph these. And yesterday we talked about how we can factor to solve these. Vertex form is what we focused on last week with our transformations. What's really nice about vertex form, it's really easy to graph from because it gives us our vertex right away. And then intercept form is really one we focused on yesterday, and that's what happens when we factor standard form. It turns it into intercept form. What's nice about intercept form is it gives us the 2 x-intercepts by taking each one of those expressions and setting them equal to 0. Remember that x-intercepts have some synonyms. Okay, they're also the solutions. So if you're asked to solve a quadratic, you're solving for the x-intercepts. They're often referred to zeros, hence this week's assignment called quadratic zeros. What we're looking for are the x-intercepts. And they're also called the roots. Now, hopefully from what I just showed you with inverse operations, you understand why they're called roots, because the inverse operations, you take the square root of both sides, and they end up being the roots of the problem. Now, finding x-intercepts, we have several methods to choose from. You can graph, okay, and that definitely works. The problem with graphing, though, is what we talked about yesterday is we don't always have nice integer answers, which aren't very easy to see on a graph. So graphing is not always going to be a great method. Plus, we don't always have access to graphing utilities. Then yesterday, we talked about factoring and how we can factor to find the solutions to put in an intercept form. Just now, I showed you inverse operations, and the next method is going to be complete the square and quadratic formula. Now, when solving quadratics, there's 3 possible things that can happen. The most common is our first graph here where there's 2 places where the graph crosses the x-axis. This is often referred to having 2 real roots. That means it crosses the x-axis at 2 places. You have 2 answers. So very often with solving quadratics, you should end up with 2 answers. But sometimes that doesn't work out. So in our next graph here, notice that it only crosses the x-axis at 1 point. This is known as a 1 double root. Okay, and what it's really kind of referring to here as being a double root is because what we're saying is the 2 points that are usually crossing the x-axis are squeezed together at the same place, and it also happens to be the vertex. Then the third situation we can have is that the graph cannot cross the x-axis at all. And this is known as having no real roots. So if you end up with a solution that doesn't have any real answers, that means our graph is either above the x-axis, never crossing it, or below the x-axis, never crossing it. Let's review factoring real quick. Remember, there's 7 steps to factoring. The first step is to go ahead and make sure that they're all in the correct order. The second step is to check for GCF. Third step is to multiply the leading coefficient by the constant, a times c. This becomes our product. Once we have the product, we We go ahead and list all the factors that can make that product. We then check the signs. Remember the second sign, the sign of our product, tells us if they're the same or opposite. The first sign is the sign of our sum. And really that's the sign of the bigger integer. So we plug in our signs on the factors, we find our sums, and we find the two numbers that multiply to be our product and add to be our sum. Once we have those two numbers, we can then break apart the middle term into those two numbers. We're breaking apart the sum, undoing the combined like term step of distribution. This should turn it into 4 terms. We then group them. So the first 2 terms are together and the second 2 terms are together. We now check for GCF on both of these grouped expressions. Then we check for a common binomial and factor that out as a common factor. What's left then is the other binomial, and now we have our factored expression. Here was an example we did in class. X squared plus 7x plus 12. 12 is our product, 7 is our sum. We find the two numbers, 3 and 4 make 7, and multiply to be 12. So we break apart 7x into 3x plus 4x. We group them, we GCF, and we find the common binomial. Again, remember their signs. For the product, if it's positive, that means that they have the same signs, either both positive or both negative. If the sign is negative, that means they have opposite signs. And the sum will tell us the sign of the bigger number, because when we add integers, the bigger integer sign is the one that carries through to the sum. So if it's positive, they're either going to both be positive or the bigger number is going to be positive. If the sum is negative, they're both going to be negative or the bigger term is going to be negative. We also talked about how we can factor with pictures. Okay, here was the distribution with pictures. And then yesterday I showed you how to factor with pictures. Now I'm not asking you to do this with your factoring, but I want you to understand the picture because it's going to come in really handy with our next method. So then yesterday we got stuck on a couple problems. X squared minus 2x minus 8, we tried to factor the pictures, we couldn't do it. X squared minus 5x plus 14, we tried to factor, we couldn't do it. So we have to be able to find another method to solve these quadratics. Now, there's a few reasons why we won't be able to factor our quadratics. One of them is that there are no x-intercepts. Remember, this was the no real root situation. This is where our graph is completely above the x-axis, never crossing it, or completely below the x-axis, never crossing it. And so no x-intercepts means we can't factor it. Well, the method I'm going to show you, and I'm going to really emphasize, is we're going to complete the square. And I'm going to show you that today. The other situation, okay, is we can't factor, is because those solutions are not nice integers. Could be that they're fractions, though those usually can be factored. But what really happens is our solutions are irrational. Square root of 2, 3 times the square root of 5, things like that. Okay, whenever we have an irrational root, we're not going to be able to factor it. So again, the method we're going to talk about how to do this is by completing the square. So let's start with a problem. We have x squared plus 4x plus 4. Okay, this we actually might be able to factor, but I'm going to show you the method with one that we could factor, just so you see how easy it is, and then we're going to get into harder ones. So the first thing we're going to do is set up our quadratic so that it's in standard form. Okay, remember degree order, and set it equal to 0 because remember when y equals 0, that's the x-intercept. That's what we're solving for. We then model that picture. Okay, so remember x squared is the big blue square. 4x's would be 4 green rectangles, and positive 4 would be 4 yellow squares. We then arrange the x terms around the x squared term. Okay, we're trying to make this a square. Okay, hence the name, complete the square. So really, to make it a square, you're going to divide those x's evenly around the x squared. So with 4x, that means 2x is going to go on the side and 2x is going to go on the bottom. That makes this still a nice square. Next, we take those 4 positives and we complete the square with those 4 positives. Okay, notice it says no 0 pairs needed. We're going to talk about that in a second. So we complete that square and we now have a perfect square. Our next task is just to figure out what makes that square. Notice that it was x plus 2 times x plus 2, also be written as x plus 2 squared. Once we've done that square, we can now do inverse operations by square rooting both sides. Square root of x plus 2 squared is just x plus 2. The square root of 0 is 0, and so we get x plus 2 equals 0. One more step to solve this problem. We just have to subtract 2 on both sides, and we get the solution x equals negative 2. This is one of those situations where we had one point where it crossed the x-axis. This is known as a double root. This also happens to be the vertex. This is for the notes, and this is the whole steps in one slide. Now let's try another one. X squared plus 4x plus 8. All right, so let's first model this situation. Take the x squared, and we'll put it right there in the corner. Then I'm going to take my 4x's. Okay, so 1, 2, 3, 4. Remember that I'm going to distribute that evenly around my x squared because I'm going to try to keep this to be a perfect square. So if I put 1 on the side, that means I have to put 1 on the bottom. Put another 1 on the side. Put another 1 on the bottom. Then I have 8 positive 1s. Oops. And my task here is I want to put in as many positives as I can to complete my square. Well, how many positives do I need? I need 4 positives. So I'm going to take 4 positives, and I'm going to complete the square. So now I have my perfect square. What will make that square? Well, I have an x plus 2 and an x plus 2. So what makes this is x plus 2 squared, but I still have a positive 4 outside of my square, so I have to write that down. So this is different from the previous example. But we still solve it by doing inverse operations. So our next step would be to subtract 4 on both sides. So I end up with negative 4 equals x plus 2 squared. I then need to undo my square by square rooting both sides. Now this is where we run into a little bit of trouble. Square root of negative 4, well, we can't take the square root of a negative number. That's an imaginary number. So in algebra 1, we would just say this has no real solutions. So this is that third situation I was talking about, where it doesn't actually cross the x-axis. It's either above it, never crossing, or below it, never crossing. Now, algebra 1, you would be done at no real solutions. But next year, when you get to algebra 2, we have to continue this and actually solve this for the imaginary solutions. So I'm going to show you that right now, just so that you're prepared for next year. So remember that the square root of negative 1 is really just an imaginary number. It's just I. So this actually turns into I times the square root of 4 equals x plus 2. Well, now that we have the I taken care of, we can actually do the math here. Okay, so the square root of 4, remember, is 2. So we have plus or minus 2i equals x plus 2. Our last step here would be to subtract 2 on both sides. And so our solution here would be negative 2 plus or minus 2i equals x. Once again, the algebra 1 solution here would be no real solutions. What that's telling us is that our quadratic never crosses the x-axis. It's either above the x-axis, never crossing it, or below the x-axis, never crossing it. But next year in algebra 2, you are going to have to do the imaginary solutions. So remember from earlier this semester, square root of negative 1 is just I. So you take that I out, and now you can do math with it. Square root of 4 is 2. Subtract 2 on both sides, we get negative 2 plus or minus 2i as our two no real solutions, or our two imaginary solutions. Once again, here's the slide for the notes that has it all in one. So let's go ahead and try another one. Okay, you can pause it here if you want to try it on your own. I'm going to go over it here just in a second. We have x squared minus 2x minus 8. So the first thing I'm going to do is take my x squared. I'm going to put it right there in the corner. Now I have negative 2x's, so that's actually going to be two of these red rectangles. I'm going to put one on the side and one on the bottom. because remember, we want to try to make it a perfect square. And so we need to keep it evenly around the x squared. We then also have negative 8. Okay, so let me grab negative 8 here. I have negative 8 there as well. Now remember, the whole name of this is completing the square. So we need to figure out how many positive 1s I need to complete the square. And the reason it has to be a positive 1 is because this square is either going to be a positive times a positive, which is positive, or a negative times a negative, which is positive. So I actually need here a positive 1. The problem is I don't have a positive 1. So what we need to do next is we need to add in something to this problem that doesn't change it. So let's think about that for a second. What can we add to something but that doesn't change our situation? We can add in 0. Remember, the identity property of addition says that you can add in 0 as many times as you want, and it doesn't change anything. But what does a 0 look like with positives and negatives? Well, a 0 is really just a positive and a negative put together. So I can add in as many of these zeros as I want, and it doesn't change anything, okay? And so I can add in a 0 to this problem, and we still have the same exact situation. But now that I added in that 0, I now have a positive 1 that I can put into my square to complete the square. So let's look at what makes this then. We have an x minus 1 and an x minus 1. So we have 0 equals x minus 1 squared. But then what do we have outside the square that we need to still add in there? Negative 9. That right there is the method to complete the square. You need to first put the x squared into your box. You need to take your x's and put them evenly around your x squared to make it a perfect square. You then need to find out how many positive 1s you need to complete the square. That's how many zeros you can add in to your problem. Then you put those positive 1s into the square. What's left outside the square, you keep outside the square. Once you have done complete the square, this just turns into an inverse operation problem. You just have to do the inverse operations to solve for your x. So in this situation, we would add 9 to both sides first. So I end up with 9 equals x minus 1 squared. Our next step here is to just square root both sides. Remember, the square root of 9 is positive or negative 3, and that's equal to x minus 1. Our next task is just to add 1 to both sides, and we get 1 plus or minus 3 equals x. Our two solutions then would be 1 minus 3, which is negative 2, and 1 plus 3, which is 4. And so our two solutions are negative 2 and 4. That means that this quadratic actually crosses the x-axis at two places, at negative 2 and positive 4. What this also means, though, is that we could have actually factored this in the first place. But let me show you a cool trick with this. If you don't want to go through the whole process of factoring, but you still need to write it in intercept form, you could actually just find the solutions first and then work backwards to find your intercept form. So what we're going to do is work backwards. Okay, so remember that negative 2, okay, is when y equals 0, what the x is equal to. So to do this, okay, we take the x equals negative 2, and we want to make it equal 0, so we just add 2 to both sides. So we get x plus 2 is equal to 0. We do the same thing for the 4. We have x equals 4. We subtract 4 on both sides. We get x minus 4 equals 0. So the factored expression here would be x plus 2 times x minus 4. This could come in handy in several situations. Working backwards from the roots is quite often how we deal with bigger polynomials. Let's try another one. X squared plus 4x plus 2. You could try to pause it here and do it on your own. I'm going to go over it in just a minute. So the first thing I'm going to do is take my x squared and put it into my box. Then I have 4 positive x's. Oops, not a negative x. Let me get rid of that. I'm going to take those x's. I'm going to put them evenly around my x squared so that it stays a square. So 2 go on the side and 2 go on the bottom. I then have a positive 2. Okay, but we also need to make sure we add in the zeros that we need. Now what I like to do is I like to just ignore that positive 2 for now and just deal with the zeros. I need 4 positive 1s here to complete my square. So that means I need 4 zeros to complete my square. So I'm going to take my 4 zeros, I'm going to add it into my square here. The 4 positive 1s complete the square. And I can now make my expression. We have x plus 2 and x plus 2. And what I have left outside of my square is a negative 2. We can now do inverse operations. I'm going to first add 2 to both sides. And so we get 2 equals x plus 2 squared. I'm then going to square root both sides. We get plus or minus square root of 2 is equal to x plus 2. I then subtract 2 on both sides. And I get negative 2 plus or minus the square root of 2 is equal to x. This is one of those situations where it still has 2 solutions. That means it still crosses the x-axis at 2 places. But the places it crosses are irrational numbers. So this is a perfect example of why we need complete the square. This would not have been able to be factored, and this would have been impossible to see on a graph. That's all for this lesson. I will continue this in our next lesson, and we'll do some more difficult complete the square problems.